Hello. In this video, I want to talk about undamped free vibration. Free vibration refers to the response of a system without any external forces. So imagine a system like a pendulum. If we were to initially displace the pendulum and let it vibrate, it would swing back and forth until there's no energy left in the system. This kind of vibration is known as free vibration. If we have a system where no energy is lost or dissipated during this oscillation, for example, if there's absolutely no friction, no air resistance, no energy losses in general, then this type of vibration is also known as undamped vibration. In reality, all physical systems have energy losses. However, in some systems, it might be appropriate to assume that this energy loss is so small that it can almost be neglected. And if we can do that, then it helps to simplify analysis of these kinds of systems. So shown here is an example of a undamped system. We have a mass M allowed to vibrate back and forth in this direction here, X, and it's resting on these rollers, which are on a frictionless surface. And the mass is connected via spring K here to ground. So you can imagine here, if we were to grab this mass M, pull it to the side, and then release, this mass would vibrate back and forth due to the spring pulling it and then compressing, pushing it back, etc. So with a system like this, we're interested in analyzing how it would vibrate, trying to learn, what kind of frequency would it vibrate, what amplitude, to be able to then design our system to have the characteristics that we want. So where do we begin to analyzing such a system? Well, the first step in analyzing a dynamic system is to develop the equation of motion. And there's several ways that an equation of motion can be derived. Energy methods is one popular way, but the method that we'll be using here and be using most commonly throughout the subject will be using Newton's second law of motion. And a general process for developing the equation of motion for a system is as follows. Firstly, we have to settle upon an appropriate coordinate system for our system. So in the past, we've talked about degrees of freedom of a system. If our system is a single degree of freedom system, then we'll need a coordinate to describe the position of, or the state of that system. So that's the first step, is choosing a suitable coordinate. Next, we want to identify what is the static equilibrium configuration of that system, and then have that coordinate be 0 in the equilibrium position. So in the example of the mass attached to a spring, the equilibrium position is when the spring is at its resting length. So we would make the position of the mass corresponding to the spring being at its resting length equal to the 0 position. So if you have a coordinate x, when x equals 0, then that's when the spring is at its free length. It's not compressed and it's not stretched. That's step 2. Step 3 then is to analyze all of the forces that are being applied to the body, and then drawing a free body diagram of the rigid bodies in the system. Lastly, once we've developed a free body diagram, we can apply Newton's second law of motion to derive the equation of motion for the system. So let's see how that works with a quick example. So here we've got a free body diagram for the mass system that we saw above. So again, we have our mass M, and that was free to move back and forth in this direction X. So this coordinate X denotes the position, but it can also be used to denote the velocity, so X dot to the derivative with respect to time, and the acceleration X double dot. And this arrow here represents the positive direction. So we're defining that as being the positive direction. We could just as easily have the arrow point to the left and say that is the positive direction. It doesn't matter as long as we're consistent throughout. So if we think about this mass moving a little bit in the positive direction, what forces are going to be applied onto the mass? Well, the spring is going to be stretched because the spring was on the left-hand side, and that's going to produce a restoring force pulling the mass back. And that restoring force will be proportional to Kx, the spring stiffness of the spring times the displacement. And because the coordinate x was defined to be 0 when the spring is at its resting length, then the stretch or the compression of the spring happens to also be x, which is why we chose that to be 0 at the spring's resting position. So lastly, we can derive the equation of motion by applying Newton's second law. So Newton's second law, in case you've forgotten, is the sum of all the forces in a particular direction is equal to the mass times the acceleration in that direction. So in this case, the mass is m and the acceleration is x double dot. And what are the forces acting on this body? Well, there's only one force in that direction, and that is this restoring force from the spring. And because that's in the opposite direction from our coordinate system, remember the positive x points to the right hand side and this force is pointing to the left, then we have a minus sign here. But we can correct for that. We can easily rearrange, putting all the terms on the left hand side, and we end up with mx double dot plus kx equal to 0. And this is our equation of motion for this system. So the equation of motion itself can tell us a lot about a system, and by the end of this subject, you'll probably be able to look at an equation of motion and tell a lot about how the system would vibrate. But it's not really the equation of motion that we're after. What we're really interested in is how this system will respond. What is going to be the motion of the mass, or x, in over time. So we're trying to solve for xt. Now, what's our intuition about how this mass will vibrate back and forth? Well, we can imagine that if this was in the real world, our intuition tells us that it will vibrate back and forth with harmonic motion. So to solve this equation of motion, which we saw was a differential equation, it included x and x double dot, well, we can start off by using a template solution, see if that fits within our differential equation, and if it does, we can solve for the coefficients of that template solution. So knowing or assuming that our mass is going to vibrate back and forth with harmonic motion, we can start off with a solution of the form xt is some amplitude multiplied by a sinusoidal function. In this case, I'll use cos for convenience, and multiplied by a natural frequency omega t with time, and possibly a phase shift of some amount. So that's represented here with phi. So again, a and phi are the amplitude and the phase of the response. So to see whether this solution fits within the equation of motion, we can take the derivative and double derivative of this and substitute it back in. So taking the first derivative with respect to time, we end up with minus omega a times sine omega t minus phi. Taking the double derivative, x double dot is equal to minus omega squared a times cos omega t minus phi. So now we've got expressions for x of t, x dot of t, and x double dot of t. We can substitute these back into the equation of motion, which, if you recall, was mx double dot plus kx was equal to 0. So substituting back into here, we end up with minus m, and then our expression for x double dot, plus k, our expression for x, is equal to 0. And we can rearrange for simplicity, collecting the like cos terms, and we end up with this expression here. So spend a second to have a look at this. Well, firstly, does our template solution, our a cos omega t minus phi, does that satisfy the equation of motion? Well, yes, it does. Substitute them in. We can see that this does in fact equal 0 if this first term equals 0. So we assume that a, this amplitude of the response, I mean, one way to make this expression equal to 0 would be to make the amplitude equal to 0, but that's a bit of a trivial solution, you know, making something have a 0 amplitude so it doesn't vibrate. Well, we're not interested in that case. We're interested in when it does vibrate. So we can assume that a, the amplitude, is not 0. Likewise, we can also assume that this cos term, cos omega t minus phi, well, as time goes on, as t goes from 0 to infinity, well then sometimes this expression here will be 0, but for the majority of the time it won't be. So if we assume that a is not 0 and this cos term is not 0, well, the only way that this expression can be satisfied is if this first term here, k minus m omega squared, is equal to 0. And if that is the case, then, well, our template solution does satisfy the equation of motion. And not only that, we can now analyze this to get a bit of extra insight. So if we take this constraint, the fact that k minus m omega squared has to be equal to 0, assuming a non-trivial solution, then we can rearrange this to solve for omega. Remember that omega is the frequency in radians per second that our response is vibrating at. And we get this result here. We get omega is equal to the square root of k on m. So what is this term? Or what does this tell us? This is the frequency that our system will vibrate at. And we can see a couple of interesting things. Firstly, it's related to the spring stiffness k and the mass m. And that's kind of intuitive. Like if we think about a spring mass system that we might have experienced in the real world, if we had a spring that was stiffer, then it has a tendency to vibrate faster. So, and because k is on the numerator of this expression, then yes, it would make the frequency higher. It would vibrate faster. And if alternatively the mass is on the denominator of this expression, if we have a system and we increase its mass, well, it has a tendency to vibrate slower. You know, it has more inertia. It vibrates slower. So this matches our intuition of how this system would vibrate. Another thing to notice is that this frequency omega here is independent of the amplitude. You know, the A coefficient doesn't find its way into this expression. And we haven't even yet talked about things such as initial conditions. So how far did this mass get moved? I talked about how if this was a pendulum or something, you know, you pull it to the side and let it go. Did I move it a lot or a little? Did I release it with 0 velocity or did I give it a push? And this frequency seems to be independent of that. And that is the case. So this term here we refer to as the natural frequency of the system, and it's a intrinsic parameter of the system. It's an inherent characteristic of the system. It's the frequency that this system will naturally want to vibrate at. And often it's one of the first things we want to know about a system, about a dynamic system. Now that we know what frequency our system will vibrate at, we can then solve for the amplitude of that vibration. So how do we do that? Well, we can use the initial conditions of the vibration. So by initial conditions, I mean when I initially displace the system. Remember, if our system is at equilibrium, like a pendulum that's just hanging there, it doesn't vibrate by itself. You have to initially displace it, let go, and it'll start to vibrate. So at that initial time, at t equals 0, it'll have some initial displacement. It might even have some initial velocity as well. If I'm not letting it go with 0 velocity, I might actually give it a push. So these initial conditions can be used to solve for the vibration amplitude. So we define the initial position as x subscript 0 and the initial velocity at time is equal to 0 as x dot subscript 0. And we can substitute these two into the time domain solutions that we had before. So this was our expression for the position of the mass, and this is our expression for the velocity of the mass. If we set t is equal to 0 and solve, we can end up with these two relationships here. The initial position divided by the amplitude is equal to cos minus phi. And the negative of the initial velocity divided by omega n, the natural frequency, also divided by the amplitude, is equal to sine negative phi. Now to solve for the amplitude in this, we can take these two expressions, square both sides and add them together, and by using this trigonometric identity, sine squared x plus cos squared x equals 1, we can then rearrange and solve for a. So our solution for the amplitude is a is equal to the square root of the initial position squared plus the initial velocity divided by the natural frequency squared. The last thing to solve for is the phase shift. And again, we can solve for this using these initial conditions. So taking the two expressions that we derived before, One had sine negative phi, the other one had cos negative phi. If we divide one by the other, we get sine over cos, and that becomes tan, and we can then solve this inverse tan to find phi, and we get phi is equal to the inverse tan of the initial velocity divided by the initial position times the natural frequency of the system. So combining this all together, we can form an expression for the time domain response, how the mass will move back and forth with respect to time. So our template solution, remember, was xt was this amplitude A times cos omega n t minus phi, where the natural frequency of the system is a simple relationship with the spring stiffness and the mass. The amplitude is based on the initial condition, so it's the square root of the initial position squared plus the initial velocity squared divided by the natural frequency squared. And the phase shift is the inverse tan of the initial velocity divided by the initial position times the natural frequency. So if we were to graph it, it would look something like this. So this is what we'd expect. So it's just a cosine response as time goes on. And the amplitude A defines the height of these peaks of the response. And this is represented with a cos function, but we can see that if it was just a cos function, when cos is 0, the output is 1, but we can see that the peak of this response doesn't correspond with time is equal to 0, and that's because there's this small phase shift here. So what this tells us about this particular response, that if we imagine this was a mass spring system that was initially displaced and let go, it must have been let go with at this position here. So this is what corresponding to the initial position. And then we see that because it's not at the peak of the response, it's actually still moving in the positive direction a little bit. There's this slope here. Then that tells us that it also has a little bit of initial velocity as well. So it actually goes beyond that initial position, reaches an amplitude a little bit beyond it, a little bit greater, and then returns back. And because this is assumed to be a free undamped vibration with zero damping, it'll continue forever. So we can try plotting this in MATLAB. I've got some MATLAB code here which will allow us to graph the response. So I've got mass is equal to 1 kilogram, the spring stiffness K is equal to 1 Newton per meter, an initial displacement of 1 meter, and initial velocity of 0 meters per second. From this, we can work out the natural frequency of the system, square root of K on M. We can work out the amplitude of the response. We work out the phase shift, and then we can simply plot it. So I've produced an array of time points, starting from 0 up to 10 seconds at small increments of 0.01 seconds. And for each of these points in time, I calculate the response of x at that time. So A times cos omega nt minus phi. We can plot the response, and this is it shown down the bottom here, and it looks exactly what we'd expect. Remember, if I go back up to what my system parameters were, we have an initial displacement of 1 meter per second. So this mass, you can imagine, was initially pulled and then released with an initial position of 1 meter. It had an initial velocity of 0. So when it's first released here, it's already at the peak of its response. There's no slope at this point. Then the mass gets pulled back towards its equilibrium position here. So initially, at the starting point here, it's at x naught here, and at that point there, it's also got 0 slope. So if I can draw this line here tangent to the response here, so it's has 0 velocity at this initial point, and then as it goes down, it'll go back to its equilibrium position, which is here, but then it'll keep going. And as it continues down here, we'll see that it'll reach the same peak, but in the negative direction. So we can play around with this a little bit. Let's try changing some of the initial conditions. So let me zoom out a bit. Now, let me change the Let me change the initial position of the mass. So I'll change it from 1 meter to 5 meters at times equal to 0. And how does that change the graph? Well, nothing much has really changed unless you notice that the amplitude, the value on this axis here, has actually changed here. So that's what we expect. Okay, what else can we try changing? I'll set this back to 1. What if we give it a bit of initial velocity? So when we first release the mass at times equal to 0, we stretch it to 1 meter, but we also give it an initial velocity of maybe a positive 1 meter per second. Let me run this. Okay, so is this what we expect as well? Here our mass initially is at 1 meter per second, but it also has, if I draw a tangent line here, it also has an initial velocity. So it's wanting to go beyond that 1 meter displacement. So that makes sense too. Let's try something else. Let's try going negative velocity. So I've initially stretched it 1 meter, but then I'm pushing it back. I release it with a bit of a push back towards the equilibrium position. And yeah, that's what we see. Still starting at 1 meter, but now it's actually got a negative velocity going back towards the 0 position. Okay, so that's playing around with the initial conditions. Let me bring it back to there. What about the actual stiffness and mass of the system? Well, we saw that the natural frequency of the system is dependent on square root of k on m. What will happen if I increase k? Let's give that a go. So I increase k. What happened? Well, now we can see that in the same 10-second time period, we now get more oscillations of our response. And this is expected. This is a system with a higher natural frequency. It will oscillate back and forth more times per second. If I go a lot higher, let me really increase it up to 20, we can see that we get several oscillations within this 10-second period. Alternatively, I'll bring it back to a stiffness of 1. Now, what if we increase the mass? So I'll go from 1 kilogram to 5 kilograms. Now we get a very slow response. Our system is responding a lot slower because the natural frequency of the system has been reduced.